This is the aerial photo of the Fukushima power plant in Japan. You've probably heard of the terrible things that happened there. There was a tsunami, tidal wave, tore apart the plant. There was a meltdown, huge fire, lots and lots of radioactive contamination. You'll note that here's the plant, and you see all these things here. Those are people's houses. Can you believe that? This huge plume of stuff that's going up, that is radioactive clouds from this huge fire. And they've had a huge effect, actually. Nobody lives here anymore, but there are a few things that grow in the area. This is an example of an ear of corn that grew there. It's a little bit strange. Here are some very strange tomatoes. Again, this is all from the radioactive contamination. But my favorite is probably this guy, the shark seagull. No, that's probably just photoshopped, but it's still funny to look at. So radioactivity. Let's just review what we know about atoms, and then we'll talk about how they get to be radioactive. Remember, when we talk about atoms, we look up here, we see the atomic number. Atomic number is the number of protons in the nucleus. We said we could write an atomic symbol. The atomic symbol was simply the symbol for the element as a superscript. In front of it, we would put the mass number. The mass number was the sum of protons plus neutrons. And then down here is a subscript in front of the element symbol. We would put the atomic number. Again, that's the number of protons. We looked at a bunch of these. Our classic example here was carbon. We said that carbon existed as 3 major isotopes, 12, 13, and 14. And these are the atomic symbols for each. They all have 6 protons. That means they're carbon. But they have, in this case, 6, 7, and 8 neutrons. That makes them isotopes. Now, radioactivity as a concept was first observed many, many years ago, 1896. Henry Becquerel, whatever, was working on phosphorescence. And as part of his work, they prepared photographic plates. Okay? Now, preparing plates in those days was not easy. These were emulsions spread on glass, and it was a real pain in the butt. Somebody, unfortunately, took one of these plates and put a little jar like this of a radioactive element, uranium salt actually, on the plate, not thinking much about it. When they developed the plate, they saw that where the jar was sitting, they had these ugly marks. The plate was fogged by the presence of this uranium salt. Well, Marie Curie and others worked on this problem, trying to figure out what the heck was going on. And finally, they figured out that there were a group of elements that would emit particles. They defined 3 of them: an alpha particle with a charge of +2, a beta particle with a charge of -1, and a gamma particle which was neutral. And these were particles that were actually emitted from the nucleus. So the nucleus spit these things out. And these little things were what was fogging the plate. Now, alpha, beta, gamma rays vary in nature and in energy. Alpha radiation. Alpha particle is heavy. It is low energy. You can stop an alpha particle with a sheet of paper. It cannot penetrate your skin. Alpha particle, really low energy. Beta particle, much more energetic. You can take a thin piece of lead, thin, and you can stop it, typically. They all vary in energy, but typically a thin piece of lead will stop it. Gamma radiation, on the other hand, is very energetic. It can travel clean across the universe. This is the background radiation that we see. It can go through 10 centimeters of lead or more. Very, very powerful radiation. It has essentially no mass, but very powerful ionizing radiation. Alpha particles. An alpha particle, like I said, is very low energy, heavy particle. We'll talk about what it's made of in a second. Beta particles are more energetic and gammas are very. We can detect their presence using what's known as a Geiger counter. Now, a Geiger counter was something that was very popular in the 50s and 60s when everybody was making bombs. It consists of a tube here. The tube, you put a potential across, and it's a very low pressure of gas inside of this. The idea is that this is ionizing radiation. So when it enters a little window here, it goes through and it creates ions in this gas. That causes a spark to jump from here to here, and when it does, you hear a sound. Oops. Come on, where's our sound? All right, well, the sound's not going to play. But if you have a compound that does this sort of thing, emits these particles and whatever, we refer to those as radioactive. The sound on my little thing here isn't working, but I just happen to have a little Geiger counter with me. And I have a jar of what's called, well, this is uranyl acetate depleted, okay? And here's the little tube right here. You can hear all the little guys coming up. Now, when most people see this and it says depleted, they think that, well, okay, it's not radioactive anymore. Well, of course it is, obviously. They actually use depleted uranium to make bullets. These are armor-piercing shells because it's so dense. It just goes right through steel. The Iraqi desert is just covered with these things, but they're depleted, so everybody thinks it's fine. It's really not. What it's depleted of is uranium-235, is what you use to make bombs. So this is 238. But we'll talk more about bombs in a little bit. All right, let's talk about these particles in general. Alpha particle actually consists of 2 protons and 2 neutrons. This is the same as a helium nucleus. Helium nucleus, helium has an atomic number of 2. Typically it has a mass number of 4. So the alpha particle is essentially 2 protons, 2 neutrons. That is a helium nucleus with no electrons. And this is spit out of somebody's nucleus. We just heard uranium decompose. This is uranium-238. Atomic number is 92. When it loses an alpha particle, it's spitting out this helium nucleus. Now, the helium nucleus has a mass number of 4. So, we start with a mass of 238, 4 of it is in our helium, 234 is left over. We also lost 2 protons, so we started at 92, lose 2 protons. If we had a periodic table, and we don't, you would see that atomic number of 90 is the element thorium. So what's happened is uranium has lost an alpha particle and formed thorium. Now the alpha particles aren't the clicks that we heard in our little thing here. Because remember, the alpha particle is so weak, it cannot penetrate skin or anything else. Can't get in the tube. What you heard here were secondary beta emissions, and we'll talk about those in a second. This is a nuclear equation. When you have a nuclear equation, the mass numbers on both sides must be the same, and the number of protons on both sides must be the same. So 92, 90 plus 2, 234 plus 4, 238. 234, we reduced it by 4. Again, the alpha particle has a charge of plus 2. Any questions? All right, let's do a quick problem. Here we have thorium-230. It loses an alpha particle. What I want you to do is write the nuclear equation for this decay. So we're starting with thorium-230. Thorium-230, 90 protons in the nucleus. This is its atomic symbol. Now we're going to lose an alpha particle. Remember, the alpha particle you can put in as the helium nucleus, 4 mass units, 2 protons. So this is going to spit out the alpha particle. When it does, our atomic number is going to drop by 2. So we're going to have an atomic number of 88. We look at our periodic table and try to figure out what is 88. Got to be here somewhere. There it is, radium. So our symbol is Ra. Our mass number, we started with 230, we lost 4, we're down to 226. Any questions? All right, let's do it again, and I'll hush, you try it. This is polonium-214, very exotic element. It also emits an alpha particle. When it emits the alpha particle, our atomic number is going to drop by 2. So we're starting here at 84. We drop down 2. Here at 82, this is lead. We started here at 214. We lost 4. This must be lead 210. Any questions? A beta particle. Beta particle consists of a single electron. It's an electron. Now, we know our nucleus is made up of protons and neutrons, right? Has a positive charge. Well, it turns out that if you take a neutron and you rip it apart, you can make a proton and an electron. And that's exactly what happens here. A neutron is sitting here in the nucleus, happy as it could be, suddenly breaks down, stays there in the nucleus as a proton, but spits the electron out. That's a beta particle. Because of that, the mass is going to stay the same, because these two masses are the same, but the atomic number is going to go up by 1. Let's look at an example. Again, we're at thorium-234. Thorium-234 emits a beta particle. So what that means is that thorium, one of the neutrons in the nucleus here, is going to change to a proton. So the number of protons goes up by 1. Now, what's atomic number 91? Let's find it. There it is, PA, Pennsylvania. So this is PA. Our mass, however, because the proton and the neutron weigh the same, the mass is unchanged. So what are we going to put here for our beta particle? Well, let's start off with a beta. It has no mass because it's an electron. But remember, this is a nuclear equation. All of these have to add up. They have to be the same. And these two, too. So we have 91 on this side, 90 here. This must be -1. Kind of strange. So it has -1 atomic number. Let's look at an example. Bismuth, 210, loss of a beta. Go ahead and write the equation. Bismuth is 83, so it's right here. Bismuth is going to lose this beta particle. 0 mass, -1 atomic number. If the atomic number drops by 1, this is going to be 82. No, I'm sorry, it's going to be 84. 84. Because we gained a neutron. It's going to be 84, so it's polonium. And again, the mass stays the same at 210. This is how you make polonium-210. Now, who cares about polonium-210? It was actually in the news a few years ago. Turns out there was a former KGB agent that the Russians did not care for very much. And so they invited him to lunch somewhere in England. And they served him a dinner, or whatever, that had a tiny trace, maybe a microgram of polonium-210 in it. and he died. Now, sit and think. If alpha particles can't penetrate your skin, how can they be so toxic? Well, because if you ingest it or inhale it, it just sits in your body, shoots out these alpha particles, and they hit the first thing that they hit, which is going to be your cell wall or your DNA or something. And they are extremely toxic. A gram of plutonium, 1 gram, is enough to kill most of the people in the world. 1 gram. And there are thousands and thousands of pounds of plutonium sitting around now. But, okay. Plutonium, polonium I mean, also decomposes, loses its alpha particle, which can be very, very toxic. Polonium is actually the most toxic of the alpha emitters. It would lose 2 mass units, 2 protons to form 82, 4 mass units here, and it's back to our friend lead. Any questions? Let's do one more. It's not just the stuff down here that can be radioactive. This is neon 19. It loses the beta particle. Go ahead and write the equation for me. Once again, we know it's going to lose a beta particle. 0 mass, -1 atomic number. That means that the atomic number here must be 11. We look at our table. Let's see, that's sodium. How about that? And our mass is still 19. Any questions? Beta particles are the ones that people normally associate with for radiation. Beta particle beams are what are used in radiation therapy, stuff like that. There is some proton therapy, but typically beta particles or X-rays are what are used in radiation therapy. Well, how do you know if an element is going to be radioactive? If the nucleus is going to be unstable. Turns out that it has to do with the ratio between neutrons and protons. These are all of the elements. This is just a straight line. This little jagged line here, those guys are actually stable. On this side, they have too many neutrons. On this side, they have too many protons. If you have too many neutrons, they tend to be beta emitters. If you have too many protons, they tend to be either positron, we'll talk about that, or alpha emitters. All these guys up here, the heavy ones, are the alpha emitters. There are also some strange ones. You can emit a proton, you can emit a neutron, a couple down here for neutrons and protons. Those are strange ones, though. Any questions? Let's go ahead and do the set. On your quiz and your final exam, you will have questions that look very much like these, where you are simply required to write the atomic symbol for the decomposition product. For our first one, we have radium. It is losing an alpha particle. This is what killed Madame Curie. Our atomic number drops by 2. Our mass number will drop by 4. We look at our periodic table. Radium is here. If we drop from 88 down to 86, we're here at radon. So radon, again, 4 plus 222, 2 plus 86 is the same as that. You may have heard of radon. Radon is the stuff that shows up in your basement. Oops. Shows up in your basement. It is an alpha emitter, and it is a toxic gas. We'll talk about that in just a second. Let's go ahead and do chlorine. This is chlorine 39. It's a beta emitter. That means our atomic number will increase by 1, and the mass will not change. So if we're here at 17, we increase our atomic number by 1, we're at argon. Lead-214 is a beta emitter. Oops. Well, you're not supposed to see this. Don't look at that.
The answers?
82 plus 1 gives us 83. The mass number stays the same. So here we are at bismuth, and we've dropped down to lead. And our last one, we have radon. Going to make polonium again. Again, atomic numbers add up, and the mass numbers add up as well. When you're dealing with an atomic or nuclear equation, simply remember, it must add up on both sides. Of course, there is a tutorial. This is the only tutorial that we have left. You can still get your 5 points, and it will be credited towards your last quiz. In this guy, we have magnesium 26 with an atomic number of 12. Now, I had to put them that way because I couldn't make it work otherwise. And we're making an alpha particle. So an alpha particle, mass of 4, 2 protons. When you work this, first thing you do, 26 minus 4 is 22. We have 12, we've lost 2. That gives us 10 as an atomic number. Then you look at a periodic table. What has an atomic number of 10? Well, that's going to be neon. And so you simply put neon in there. Again, 5 questions, 5 points. Practice them. They're kind of neat. Any questions?
Yeah, don't change it yet.
All right, we talked about radioactive decay. We've done uranium and thorium and all of those guys over and over again. That's because as these things decay, they can emit alpha particles, which will decrease their mass, and beta particles, which will increase their atomic number. So here for plutonium, we can lose a beta, go up to americium. We can lose an alpha, go down to neptunium. Lose another one, go down to protactium, something like that. Lose a beta, go up, go down, go up, go down, etc. That's the process of nuclear decay. Let's look at one that we've talked about, and that is our friend uranium. This is uranium-238. As we saw, it can lose an alpha particle. When it does, its mass drops by 4 and forms thorium. Thorium, in turn, can lose a beta particle and go up here to form this same atomic mass, but different atomic number. This then loses another beta particle, and we're back to uranium. This can now lose an alpha, and we're at thorium. Lose another alpha, we're at radium. Lose another alpha, and we're at radon. Now we talked about radon. Granite contains traces of uranium, natural uranium. Because of that, this decay process goes on constantly. If you have a building or something that is built with granite or on granite, you're going to be going through this decay until you hit radon. Well, radon is different than all the others because it's a gas. So when you hit radon, it starts to seep out of the rock. That's radon in your basement. And you do these little things, radon testers, that you have to do these days to prove to the inspectors that you don't have radon in your basement before you can sell your home. Remember, you can't just go down with a Geiger counter because the alpha particle can't make it through the window, so you have to use the actual detector. When they mine uranium, they take lots and lots of granite and they grind it up and they extract it and whatever, and they're left with what are called mine tailings. There's huge mountains of ground up granite. Well, what do you do with those? You make bricks out of them, right? And what do you do with these bricks? Well, you build UIC with them. The walls, floors, everything at UIC are built with mine tailings. In fact, you can take a detector and stick it up against the wall, and you can detect alpha particles. Whatever. It was cheap, I guess. The concept of half-life. As these elements start spitting these things out and changing, they're changing from one element to another, right? How long does it take to do that? Well, that's measured in what's called a half-life. If you start off with 100% of something, the time that it takes to drop to half of that is defined as a half-life. Radioactive decay follows this type of curve. The half-life, again, is when you go from whatever you start to only half of it. Look at strontium-90. Strontium-90 emits a beta particle, forms yttrium. The half-life here is 10 to the 6 seconds. That's about 30 years. Now, why is that important? Probably not so much to you, but it was important to me in our day. In the 50s, people were exploding bombs in the atmosphere everywhere, just for fun. One of the products of the nuclear fallout was strontium-90, okay, beta emitter. Strontium-90 is isoelectronic with calcium. And it would like rain down on, say, Wisconsin, where they made milk, which is rich in calcium, right? And so they served strontium-90 milk to a generation. Now, Fortunately, after 30 years, half of it's gone. 60 years, 3/4 of it's gone. There's still a little bit of it hanging around. But yeah, that wasn't a good thing. Let's look at cobalt-60. Cobalt-60 is used as a radiation source for therapy. Half-life of 5 years. If we have 1 milligram, after 15.9 years, how much cobalt-60 do we have left? Now there's a formula. We're all tired of formulas. Yes, you are. All tired of formulas. We can do this in our head. When we start, we have 1 milligram, right? After 1 half-life, we have 0.5 milligram. After 2 half-lives, we'd have 0.25 milligrams. After our 3rd half-life, we would have 0.125, actually 0.13 milligrams left. When I first gave this lecture here, I asked if they had any radioactive samples for my little Geiger counter. And they handed me these cards with cobalt-60. And I said, oh great, took them up in class, did this, nothing happened. Why? Because they were dated 1965. So everything was gone. And I suppose that's good, considering. Just as an example, uranium, 10 to the 9th years for its half-life, long time. Thorium, 10 to the 10th years. Carbon-14, we'll talk about this, 5,700. Strontium, like we said, to about 2830. Iodine, when 3 Mile Island blew, in this country we had a meltdown. There were clouds of radioactive iodine that were released. Very bad stuff. It's bad because it's absorbed by your thyroid. And it just sits there in your thyroid and radiates you. So you take iodine pills to counter that. Fortunately, it has a very short half-life, so it's all gone. Carbon-14. This carbon-14 story is actually kind of neat. In the upper atmosphere, we have nitrogen N2 floating around, and we have energetic particles from the sun. Nitrogen, it turns out, can absorb a neutron from the sun. So this neutron comes, hits the nucleus, sticks, just for a microsecond. We form nitrogen-15. Well, that's really unstable. What happens is it breaks down instantly, ejects a hydrogen atom, and forms carbon-14. So this is going on way up there in the upper atmosphere all the time. So the air that you breathe, everything that you eat, whatever, will have a fixed ratio of carbon-12, which is what we have, and carbon-14. It's always a fixed ratio. Until you die. Now, carbon-14 breaks down again to form nitrogen, emits a beta particle. Half-life, 5,700 years. Now, as long as you're alive, you're breathing and eating a fixed ratio of carbon-13, of carbon-14, carbon-12, right? When you die, you stop eating and breathing. And so you're not getting any more carbon-14. So the carbon-14 that's there starts to decay. What you can do then is measure the ratio of carbon-12 to carbon-14 in a sample. And it will tell you when you died. This is used in radiocarbon dating, fossils, stuff like that. Perhaps you've heard of the shroud thing. The shroud is supposedly a burial cloth from 2,000 years ago. It has been examined many times using carbon-14 dating, etc. Unfortunately, the samples that they would let them take were only from the corners, and so it's argued that the dating was imprecise. You can't really take one from the middle of the image, but this is used for dating old bones and stuff like that. It's actually a very, very useful technique. You've heard of antimatter, I'm sure, if you ever watched Star Trek. Antimatter is just the opposite of everything that we know. A positron, this guy, is a positive electron. It turns out that a proton, if it feels like it, can eject its positive charge as a positron and turn itself into a neutron. Carbon-11 ejects a positron and forms boron-11. So the proton simply turns into a neutron and ejects the positive charge. Kind of strange. Positrons really don't belong. And if a positron, which is a positive electron, happens to hit an electron, think about Star Trek, you have matter and antimatter, and they're kaboom together. What happens? Well, you get formation of gamma rays. These gamma rays are actually ejected from the position of the electron in opposite directions. Now this might sound a little esoteric, but this is how you do a PET scan. Turns out that fluorine-18 ejects a positron from oxygen. And as it does, the gamma rays are ejected opposite directions from wherever they happen to hit an electron. So you take somebody and you infuse them with glucose, actually. Glucose is labeled with fluorine-18. And as it's sitting there in your brain or your body or whatever, it's going to eject these gamma rays, which are measured by this array. From computer technology, you can move this ring back and forth over people and come up with a whole image. And this is a PET scan. So this is where the fluorine-19, fluorine-18 is concentrated in this poor woman's abdomen. Any questions? All right, nuclear transmutation. Well, we talked about that quickly with carbon and nitrogen and carbon-14 formation. This example is the same sort of thing. Aluminum-27 can also absorb a neutron to give a transient aluminum-28. But once it forms, these elements are very, very unstable. When you get a really unstable nucleus, it tends to split in half. With aluminum-28, it splits into helium and a sodium. Well, okay, that's interesting. Nuclear fission, however, does other things. This is an artillery piece, and it's firing a small nuclear weapon. Straight from the barrel of this little guy. This is the initial shock wave. See it coming? These things are placed about a mile from where it landed. And here are these guys sitting back here taking pictures. They're probably dead by now. The yield from this weapon was about 1 kiloton. One. Hiroshima was about 13, Nagasaki was a little more. This is 1.
Isn't it crazy how all those people that were like there
Yep.
didn't think that there was anything that was
There's nothing wrong with sitting there. This is what it looks like in real life. This is the actual warhead itself. And these guys, see the pocket protector? These are the guys that designed it. They're very proud. You can fit this in your backpack. In fact, we can make them today that fit in a soda can. Yeah, that's 1 kiloton. Now what's happening here? We have an element, uranium-235. Uranium-235 is what you think of initially when you think of an atomic bomb. It's an element that is very prone to undergoing fission. Uranium-235 can absorb a neutron. Remember we saw aluminum, it forms this odd nucleus and then splits. Same thing happens with uranium. Neutron comes flying in, hits the nucleus, and it splits. It evolves a huge amount of energy. And as it does, it releases 3 more neutrons. These 3 neutrons, in turn, hit 3 more atoms of uranium-235. They split, and you get 9 more neutrons. They hit others, etc., etc. That is a nuclear chain reaction. Nuclear chain reaction, one of the classic ways to demonstrate this is using ping pong balls. Here's a cage full of mouse traps with ping pong balls. Let's see if we can back it up and do it again. When you drop the first one in, it sets one off, and then boom, they all go off. Oops, there you go. That's a nuclear chain reaction. So, uranium-235 absorbs a neutron, gives 236. It's really unhappy. That splits to barium and krypton and kicks out 3 neutrons. This is the principle for the bomb. It's exactly the same principle for a nuclear power plant. The trick to doing this and controlling it is to make sure you can absorb these neutrons so that they don't just keep going and hitting more uraniums. To do that, you use control rods. These little control rods go down, they absorb the excess neutrons, put them down, you can shut it off, pull it out, it goes. The real problem with a nuclear power plant is that if something goes wrong with this mechanism and it's stuck open, then there's no way to control it. It just melts down, just gets super hot and boom. Now, how do you do this if you want a bomb? This is what's called a gun-type bomb. This was the very first atomic bomb. It is so simple. We could build one right here on this tabletop. It is so incredibly simple. And that's what's scary about it. It is so simple. Only thing is that getting uranium-235 is tough. If we had uranium-235, roughly 35 kilograms, we'd be good. What happens? You have basically a gun barrel here. You have a lump of uranium at this end. You have a lump of uranium at this end. Now, in order for the fission to happen, the total lump of uranium has to be large enough so that the neutrons you form don't escape. That they're going to go and hit another uranium before they get out of there. That's called a critical mass. The way this works is you take half of the mass here, half of the mass here, slam them together. Wait a microsecond, and you get your explosion. So let's look at it. We set off basically an artillery shell here, shooting this thing down the barrel, forms a critical mass at this point, and it goes off. This is the bigger bomb. This is roughly, I'd say, about 12 kilotons. So about the size for Hiroshima. Now that's the way you used to make them. Today, everything is much more sophisticated. Today, nobody wastes all that 235 to make a bomb like that. Today, you use what's called an implosion device. Typically, you will use plutonium instead of uranium-235. This little ball of plutonium is about the size of a softball. You wrap that with high explosives. High explosives shell around it, makes it about the size of a soccer ball. Now, this is subcritical, so we're not at critical mass here. The idea is to set off all of these explosives at once so that you squeeze the plutonium down. It increases the density. When you increase the density enough, you hit a critical mass, and boom, it goes off. Call it an implosion bomb. This is how bombs are made these days. Interesting thing. This little thing here, the little round guy in the middle of the softball, is called a plutonium core, right? Now we all know that we're under international agreements that we can't have, we can only have so many bombs and blah, 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 right? But that doesn't apply to cores. So the United States has a certain number of bombs put together, and we have 30,000 cores sitting there on the shelf. and 30,000 explosion devices sitting next to them. Israel has probably 1,000, but they're not put together, so they're not bombs. Russia has as many as we do. And a lot of theirs are missing. That's one of the real problems.
Why? Why are the bombs missing?
Why are they missing?
Yes.
Because when the Soviet Union went under,
Yeah.
they were left totally unguarded all the time. And people picked them up.
Yeah. Did you hear about the bomb they tested a couple weeks ago? What's it called? Anyone know about that? Like the Trump administration, like they had like some bomb they tested a couple weeks ago. I forgot what it was. It was like a bomb.
Oh, no, that's a ground.
Oh, what is it?
It's an implosion bomb. It's probably low yield, probably 15 kilograms. And it's designed to dive underground
Crap.
and get way underground for it.
Okay.
So it's really a hard report.
Okay.
All right, so fission is kind of the easy guy. Let's talk about fusion. In fusion, you're going to take two happy little nuclei and squeeze them together and make one. When you do this, the atoms are very unhappy and they emit a huge amount of energy. Here we have hydrogen gas and tritium gas. So this is hydrogen with one extra neutron. If you squeeze these two together, you can form helium and you emit a really, really high energy neutron. And lots and lots and lots of energy. This is what's behind a fusion bomb. This is how the sun works, sort of. The sun actually takes hydrogen, squeezes it down, makes deuterium, and eventually makes helium. And at every step, you're evolving energy. So this is the process that drives the sun. Gravitation in the sun squeezes the hydrogen, forms it to form helium, and therefore will warm. In a fusion bomb, you know when you have a bomb you want to set off, you need a detonator, right? Something to get it started. What do they use in a hydrogen bomb to detonate it? They use a fission bomb. So there's an atomic bomb that goes off first that starts the whole process. So you have your atomic bomb up here. This is an implosion device. And you have your tritium and hydrogen down here. You get huge neutrons formed up here. They reflect, compress, and you get an explosion. The explosion is not minor. This was the first fusion bomb tested. It's amazing to watch. We've been seeing things that were roughly 10 or 12 kilotons. This is 10 to 12 megatons. Back in the 60s, many people don't know this, but the Soviet Union had probably 4 of these guys aimed at Chicago. Because their guidance was so bad that they weren't sure they could actually hit Chicago, so they had 4 coming in. Huge ones. And to counter that, Lakeshore Drive, we all know Lakeshore Drive, right? There were missile batteries on Lakeshore Drive. And they each had 10 kilotons atomic bombs on them to shoot up and try to knock these things It's a wonderful time to be alive. The biggest one ever exploded was a 50 megaton device. The Russians did it. Originally, they had designed it to be a 100 megaton device, like the mother of all bombs. But they decided that the plane dropping it could not get away fast enough. Here it goes. This is a 50 megaton device. This mushroom cloud goes up 40 miles into the atmosphere. One massive explosion. Well, like we said, nuclear fission isn't just for bombs, it's also used to make power. This is a standard power plant. This is just a cooling tower because you have lots of hot water, sprays over it, and you get lots of steam coming out. Here's a reactor building right here. The way a nuclear power plant works is actually fairly simple. You have the control rods, like I said, you have your stuff, your core, and you move the rods up and down to control how fast the fission goes. It gets very, very hot. You have water that flows in and out. You have a separate container where this water then heats a second group of water, flows in and out, turns a turbine, and you make electricity. To cool this down, that's where you use your cooling tower. The problem, of course, is that if something goes wrong with your control rods, this core will overheat, and when it does, you get something like this. There's another problem with nuclear power plants, and that is even if they work well, even if everything is good, eventually you're starting to run out of 235. So you've got these rods and you have to do something with them. So what do? Well, obviously, you build a big swimming pool and you put these rods in there. Now, the rods are hot, so you have to pump the water out, you have to cool the water, pump it back, etc., etc. If something happens to the water pump, these things will melt down just like a reactor will. Not good. You can also take it and try to bury it. Look at the size of this truck and these canisters. These are on their way to someplace, I think, in Nevada, where the government spent several $billion digging a cave complex, and then decided that it was on an earthquake zone, so it wasn't a good idea at all. These things, there's thermal imaging, they're hot, and the idea is just to let them sit there for, what did we say, 10 to the 10th years, until they finally cool off. That is a problem. So most of it actually is stored in swimming pools. If you look at the map here, these are metric tons of used core that are just hanging around. Let's see. Florida has 3,100 metric tons. None in Wyoming. Colorado only has 30. Texas has 2,300 metric tons. Who's the winner here? 9,290 metric tons of used core sitting in swimming pools out in Morris. Wow.
Didn't we invent, like, not us, but like, the nuclear bombs invented in UIC?
Not at UIC, at UFC. Yeah, that was the first fission, first controlled fission. They were actually very, very worried when they did that. Everybody in the group knew that they were going to be able to control it. But could they be wrong? What if we pulled out the control rods and then we stuck them back and it didn't stop? And what did they do with the entire apparatus when they were done? Well, they took it, they buried it way out in the far boondocks where nobody's ever going to go, right? The Payless Heights. Yep, it's still buried out there. All right, fusion. You know, fusion is kind of neat. It's a neat concept. You get a whole lot more energy out. Obviously, the bombs are bigger. But it's a really tough thing to do. We don't have a whole lot of uranium-235, but we have lots of hydrogen. Okay? So if we could use that as fuel, that would be good. Again, the plants are designed to take hydrogen and tritium, push them together, make helium, high energy neutron, and lots of energy. In order to get this process to happen, you need, well, this is the original version of a fusion reactor. Of giant magnets in here. You set up a plasma, so super, super hot gas with the hydrogen and the tritium in there. And under high pressure, they will fuse. Problem is that this takes more energy to run than it produces. And so that's bad. This is what the thing looks like. Again, here's our plasma chamber. We have magnets all around it. The plasma goes round and round and round. Fusion happens here, and you recover your energy. Basically, it's exactly like, well, a coal-fired plant. You're going to take your plasma, your hot plasma, take the hot fluid, heat exchange it, turn a turbine, and make energy. Now, people have been working on this for a long time. There's a really interesting effort underway now to use lasers instead of the heat from the plasma to initiate the fusion. So we have a huge array of lasers, all focused on a spot, and you put a tiny droplet of hydrogen and tritium there, and they undergo fusion, and you can recover some energy. The latest advance is this guy. This is being built by Lockheed. It's a concept. It's built by Lockheed Skunk Works, it's called. Okay. This thing literally is laser fired, and it literally fits on the back of a truck. Produces 100 megawatts. Now, you could use one of these guys to power a ship, even power an airplane, spaceship, anything like that. They're actually quite small. They're getting close. I don't think they've actually got to the point where it's fired and producing more energy than is being put in, but I think they're getting really close to it. This is probably the real future for fusion power, are the little mini things. Now the little mini things, but they're not trivial. The shielding that has to go around it to protect everyone from these neutrons is stainless steel, about a yard thick. So a giant sphere of stainless steel surrounding the reactor in the middle. But it does seem to work. Well, hopefully it will pan out to work. Any questions? All right, chapter 12 is Earth Science, and we will do that on Wednesday, and then we will have our third quiz, and our bonus lecture is going to be nutrition. Have a good evening.